boundary operator. So the boundary operator. The boundary operator is defined as follows. Okay, so let me first write how it is denoted. It is denoted by some sigma n, and this is called the n boundary operator. So what does the boundary operator tell us? Well, if you have a simplex like this, let's say a triangle, filled in triangle, and you write the simplex for it, what the boundary operator does is that it acts on the simplex and it spits out the boundary. Okay, and I also want to give you a warning. Do not confuse the boundary operator, that is del n boundary operator, with a partial derivative. Even though they are both denoted with dels, do not confuse them, because these two means totally different things. Okay, so this is a warning. So in this set of lectures, we'll just, whenever we write this del of n, you will understand that this is a boundary operator. We're talking about a boundary operator. Okay. Okay, now let's define it. So definition of a boundary operator. The boundary operator is defined as follows. Is defined as follows. Let's say you have some n chain, which is also a simplex, the sigma n. The n boundary will act on this and it will produce something like this. 0 to n, let's say. There is -1 over, there is an I in the power, and you have this p0, p1, da 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 da. There is pi, and there is a hat over there, and we'll explain what does the hat mean, and we'll have p of n at the end of the day. And this hat means that the element under it should be omitted. And let's see an example that will clear things more for us. So let's say this is an example 1. Let's say we have some sigma 1, which is a 1 simplex, denoted by p0, p1, which is just a line, and we want to compute the 1 boundary, denoted by del 1. So del 1 sigma 1 will be given by del 1, and it will act on p0, pi. And by the definition we saw a few seconds ago, this is written as I from I equals to 0 to 1, right? And it told us that it should be p0, p1, but there should be some hat, and that hat will indicate that the element under the hat should be omitted, right? So if I write down this thing explicitly, it will be when I equals to 0, I'll have -1 over 0, and I'll have a hat over p0, and there will be a p1, then plus I'll have a -1 over 1, and I'll have a hat over p1. Now the hat tells us to omit that element, so this is just 1 times p1 and this is a minus P0. So the boundary operator acting on this simplex, this one simplex, will give us this. Okay, and this is in fact the boundary of this one simplex. And we want to also make a comment that if I had a zero simplex, let's say some Pn, or okay, let's just write this as P0. This is a zero simplex, right? So whenever the boundary operator acts on a zero simplex, it produces 0 because the point doesn't have any boundary. Okay, let's take a look at another example. Example 2. Let's take this triangle for a reason. Let's say this is P0, this is P1, this is P2, and I introduce the counterclockwise orientation. So the simplex itself is a 2 simplex, which is given by P0, P1, P2. And now I want to compute the 2 boundary, del 2, sigma 2. So this is del 2, P0, P1, P2. Now I can, again, you can start with the summation, or you can write it out directly as well, but let me just use the summation notation that we used, and let me break it down explicitly. So when I is equals to, we write it as what? 0, 2, 3, because there, sorry, 0 to 2, not 3. So under this summation sign, there will be a minus I to the power I, and let's say there will be P0, Pi, which I should be emitted 1 and 2. This is the, let's say this is the running index that we're working with. So if I expand out this summation, then this is just minus 1 over 0, P0 hat P1, P2, plus minus 1 over 1, P0, P1 hat P2, and then plus minus 1 squared, P0, P1, P2 hat. Hat means omit that element, so we finally write it as P1, P2 minus P0, P2, and we write it as the final one as P0, P1. Now note that we can stop at this point, or we can make things a bit simplified as well, is that we introduced an orientation, right? So this P0, P2, P0 is over here and P2 is over here. So P0, P2 means going in the opposite direction of the given orientation. So we can absorb that minus sign and interchange P0 and P2. So I write it as P1, P2 plus P2, P0 and P0, P1. Now look at the orientation. P1 to P2 is along this orientation, that means along this line. P2, P0 is this way, and P0, P1 is this way, and they match with the given orientation, right? And this is the boundary, the 2 boundary of this triangle. So you can see intuitively that on this case we got an intuitive result. That means if it's a filled-in triangle, otherwise we wouldn't have this one. So in this filled-in triangle, the arms are indeed the boundary of a triangle, but for a line over here, the one boundary is not very intuitive. So this tells us that the boundary is not always that intuitive. Okay. And if you wanted to compute, let's say, the one boundaries, then that means you want to compute this del 1 sigma 2, that wouldn't have an intuitive explanation as well. So for now, if I have an n simplex, I want to compute the n boundary. For now, we want to only focus on this one. That means I have a simplex, I just want to find out the boundaries. Okay. So from these two examples, we can say that in general, my boundary operator will act on the set of n chains and produce elements of a n minus chain, n minus 1 chain. Because those simplexes are, at the end of the day, they form a chain group as well. So that's why I'm writing it like this. It acts on the elements of the n chain group and produces an n minus 1 chain group. Okay, and I want to make a comment right now. This is only for your information. It can be showed that applying the boundary operator twice, which we also denoted del square, it's always equals to 0. And it has a very famous explanation that the boundary of a boundary is 0. This is something you will probably see in your general relativity course, so I don't want to stress this factor over here. So now we want to see that how this chain complex actually works. Is that, let's say we have a n-dimensional simplicial complex that forms a n chain group. So let's denote that with C of n of k, and then if I apply the n boundary operator, I have some Cn minus 1 of k, right? And then I want to find the boundary of the n minus 1 chains. So what do I have to do? I have to apply the boundary operator again. I have C of n minus 2, and then I apply del n minus 2 again. I have what? C of n minus 3, and so on. So I can do this up to n times, and what I'll finally have is something like, let's say, del 2. Here is C2 of k, 2 chains or 2 chain group. I have a 1 chain group. I apply the 1 boundary operator. I have C0. And if these C0 chains are made of only 0 simplices, right? By the definition that we gave for the n chain groups. So if I put n equals to 0, I only have elements that are points. And we said that whenever you have a point and you apply a boundary operator on it, it gives you a 0. That's the definition of a boundary of a point. So I can apply del 0, and then I can finally get a 0. So this structure is often called the chain complex. So if you choose any n chain, and okay, let me write it down. So this is another comment. If we choose any n chain, that means the n chain is just an element of the chain groups. Then we can say that many, but not all of them, of these C, small c, that means the chain which belongs to the capital C n, the chain group, can be written as the image of some other element. Let's call that C prime, that belongs to C of n plus 1, through the help of n plus 1 boundary operation, or the n plus 1 boundary. Now if we get any such c, that means small c, this one, such that the n boundary is 0, then we call them n cycles. If we have a n chain, C is n chain, and apply the n boundary operation on that chain, and if I get a 0, then I call them n cycles. The set of all n cycles are written, so let me write that down. The set of all n cycles are written as Zn of k, and this is a subgroup of the chain group, the n chain group. Okay, so if you take Z0 of k, you will notice that this Z0 of k only contains 0 chains. And since C0 of k are also C0 of k also contains 0 chains, and let's say for some C prime or C double prime, let's say, just to distinguish things, where C double prime belongs to C0 of k, that means any type of C double prime you take, those are just points, like this can be a C double prime. Okay, so these are my n cycles, right? They're 0 cycles. So all the elements on C0 and all the elements are Z0 are the same thing. So we write it as Z0 of k is equals to C0 of k. Okay. So this is our discussion on the chains, and now we want to define formally the idea of the n boundary. So